Good afternoon, ladies and gentlemen. My name's Alex, and welcome to my game dev channel. Several weeks ago, I promised to publish the video about the optimization in procedural world generation, and I promised to show you how to add multithreading to our procedural generation and some load system. Actually, it took much more time than I expected, but with help of my friends, uh, I have done it. And actually, talking about the load system, uh, I decided to not show you this system because, in my opinion, this is not the most important part of the optimization. And in many procedural generated worlds in different games, you can see that these games actually don't have any dynamic load system for the landscapes. Actually, they have load system for the objects, for the items on these landscapes, but not actually for the landscape. The reason for that um, is because this is not optimal. Actually, uh, maybe load system can improve the performance in the actual and endless world, literal, but often when we do our chunk system and when we try to make render range of these chunks, uh, these numbers actually don't too big, don't too large, and there is no reason to create additional load system because if we have no much chunks, so we don't need the load system because any modern computer can calculate everything. But what is important here is multi-threading because procedural generation is always um, a lot of numbers, a lot of calculations, and we can't actually ignore the fact that while these calculations is going, our main thread actually usually just stops and we can't do anything else. So it's really important to make every calculation in different threads. So that's what we've done here, and I'm gonna show you how to achieve it because it's actually quite difficult for those people who don't understand C++, for example, or actually Unreal Engine framework. But before, let's see what we have. As you can see, here our landscape generates during the time from the center, from our player, um, like one chunk per frame. And here, as you can see, we have a really detailed mesh and a lot of chunks. If we go forward, actually let's fly, you can see that new chunks automatically loaded, and the loading one chunk per frame. I hope you understand what I'm talking about. Actually, such system we can see in Minecraft, for example, and some other games maybe. I actually don't know many games with procedural worlds. And as you can see, we have no problems with FPS, and we can go forward smoothly without any freezes or lags. So I can see, as you can see, this system works well. But the one thing you may mention that the chunks behind me don't remove. This is because I want to show you in the next part of the video the system which can help us to cache data actually, and when we come back we will load this data from our cache file, and it will help us to save everything that there is in that chunk, and we can load it back instead of just removing it or hiding it, because hiding takes much of RAM, but removing just removes everything, and we will recreate this chunk from absolutely scratch, and so any data we change there will be removed. I hope you understand what I'm talking about. So let's stop it and see our code. So here, as you can see, we have, maybe you can't see, let's close the game. We actually have two files. Endless generator. No, not two, three files. Endless generator. You can see it here. Mesh data. This is our structure we can use to push inside our chunk class. And actually our chunk class. Where is it? So here. Let's clear up. Okay. So let's start from the main and the most important file, endless generator. Here is the header. In the header you can see a lot of variables. Actually, all these variables needed to change the noise data in the game. I will not talk about it because you can see all of them in the previous videos. So let's see what we have here. And actually here we have several important variables. The first one is a chunk mesh pointer spawn actor. This actually is a chunk will spawn. Then this variable is needed to understand that our player is moving and change its coordinates. This variable, actually tmap, contains the key value as a f vector, and so the value of fmap data. We call it map cache, and we will push this variable in our chunk mesh class. Here we have another variable, but actually we don't need it in this tutorial. Then this variable can be deleted, but you could ignore this variable. Here in the protected section we also have some variables for our generation, like curves and noises. And here's a lot of functions, helping functions and main functions. The main functions generate chunks. Let's see what this function does. Let's open endless generator. And here, as you can see, even begin play, we set up our noises. It's fractal types. So setup noise is the function, helping function. You can see it here. I showed in the previous videos. Let's close it. And even begin play, we generate chunks. Let's see what generate chunks does actually. Here we have a couple of local variables like chunk chords, locations, the very important array. Player location, we get player location once we call this function method. Here we have the number of vertices per line and the calculation of it. just for convenience, we get chunk size divided by grid spacing plus 1. It's important to add this number. So, and then we have actually our generation. First of all, every call of this function, we have to understand what are the locations for our chunks. And these two loops actually does it. Here you can see that we calculate our current chunk coordinates for current chunk and calculate the chunk location using these chunk coordinates. This function, actually, you can see it here. Get current chords, get the player location every time we call this function, and get the x and y values, which is actually the integer, rounded integer, equals player location divided by chunk size. So we got the coordinates of the current chunk. And then, after we get them and add x and y, we can actually calculate our chunk location and different helping variables. Chunk vector length needed to generate chunks not in a square but in a circle. And this check actually does it. This variable needed to understand the actual radius of our render range, to understand if the distance to a chunk more than this value of radius. And distance to chunk actually calculates the distance between our actual chunk location and our player location. I don't use it here, but you can use it just for destroying chunks and removing them from arrays. So every time we call this function, but here, as you can see, there is no logic for that. But this important check also checks if our map cache contains this chunk location as a key. And if it not contains so any data, we can add this data in this map cache. So not in map cache, but in locations. This locations variable, if you understand, becomes empty every time we call this function. So, but map cache contains data always. And if we understand that in map cache there is no such location, we can add it in locations array. But why we need it? Because then we can sort this locations array depending on the distance between the actual chunk and the player. And we can so this is needed because we want to generate chunks from the center, from our player to the edge, but not from some edge to the other edge, if you understand what I'm talking about. And after we sort it, depending on the distance, we can actually make another loop, and here we create our fMapData object using constructor, and then add in our map cache our locations, sorted locations, as a key, and in each key we can put our map data, empty map data. Then we can use this spawn queue variable. Actually, I don't talk about it yet. Let's see here. As you can see, under the map cache we have tq. Tq is a special variable which we can use to for our multi-threading and for using the data in this queue to generate our chunks in the duration of time. I hope you understand what I'm talking about. If not, I will show later. Here we add in this queue with this special method in queue our location. And then that's all. We generate our locations. It's so not expensive operations. There is no expensive operations here, but then we have to do several things. First of all, we create mutex. Mutex is needed to prevent data changing in the other threads. It's really important. Otherwise, we will get crashes, maybe something else. So never try to change data in different threads in one time. Then we use parallel for, actually not function, but so you can read what this thing does. Actually, it helps us to multi-threading our chunks, to generate mesh data in different threads and creating a pool of threads, thread pool, where we put our data in, and then in different threads all this data calculating and come back to the main thread, and then we can render it. What is important here to know is that we can't render actually anything. We can't work with render, with graphics, with meshes in the other threads, because such operations should be in the main thread. But we can calculate everything in the other threads, then get back data and use this data to actually render our meshes. It will lead to freeze if we'll do it immediately, but if we will render our meshes during the period of time, so we'll get a really interesting result you saw before. So what we do here, we get the location of locations. Actually, we use it locations num. I mean the size of this array as a number of calls of the code which is inside this parallel for method, let's say method. So, and here we get automatically location of the locations in each index. You can see here index. Then we create empty arrays for vertices, triangles, and so on. Create a special vertex variable for our generation. Here we have mesh simplification for load system, but we actually doesn't do any loads here. You can remove it, but I don't recommend it because here I use it anyway. So here we just generate every things. We calculate our mesh data. You can see how we do it in the previous video actually. I will not stop in here. But what we have to understand that here we calculate different values and putting them into arrays. And after we did it, we calculate targets for mesh actually as well here. And then we lock our mutex. And inside this mutex, not mutex, between these two operations, we have to put our data inside our map cache. And as you can see here, I get our map cache in a using location as a key. We get location here if you don't forget about it. And there, when we get actually the variable of this structure, we can put our vertices here. So after we've done it, we can unlock our mutex. It is important. So after all, we can hide it. After all, we have to do several things. event begin play, we call this function and it generates data, put it inside um, the map cache, but we also have to put this data in our chunk class and spawn this class and generate and create the mesh of this class. So before, let's see how actually our chunk mesh looks. Here you can see a bunch of includes. Most of them we don't need it, but here what we need is procedural mesh libraries. Actually, we have to directly include this procedural mesh component and material interface. It's important too. So here we declare this procedural mesh and material, and inside our CPP file we can firstly create default sub-object procedural mesh, set it as a root component. It's important. Set shadow as false because we don't need shadow of our chunk. It will lead to many glitches. Here we can change the visibility, but is the rudiment, we can ignore it. And here we have a function, as well as here. You can see create mesh. This create mesh function actually get our procedural mesh and using this method create mesh section linear color, which is not deprecated. We can push the vertices, triangles, normals, and so on from our map data, which is our argument of this method. And then we can set up our material here. That's all for this function, for this class and this function. We can close it. It's really easy. But what we should do in our endless generator is actually to see this event tick. Event tick, first of all, let's talk about the check. We check on event tick, we check if our coordinates don't changed. So 1 second, please. Actually, we check if our last coordinate equals our current coordinates. If it's true, it means that coordinates not changed. But if it is, if it doesn't, it means that coordinates changed, and we have to update them and call our generate chunks function. What we actually done here, we update our last coordinates, make them equal to our current coordinates, and then we call generate chunks. So let's close it. The name of this method isn't right. But what is more important is this method, create class and mesh. We call it every tick, just every tick without any checks. And what actually happens here is when we call this method, we first of all declare our local q item variable, which equals f vector, because our tq also contains vectors, f vectors. And here, if our spawn queue isn't empty, and if spawn queue can dequeue item, dequeue means we can get this item back from this queue and remove it from this queue. So actually this method does this thing. You can read it again, removes and returns the item from the tail of the queue. So we get this queue item, and then we spawn our actor in the world actually. So we get world, spawn actor, a chunk mesh, and here I put chunk, which is actually the sub-object class of a endless generator. Here I declare it. We can inside the editor choose which class we actually want to spawn. For example, we can create a blueprint representation of this class and put this blueprint class inside inside this like how to say, let's say row, maybe, I don't know. So I hope you understand what I'm talking about. I will show it later. So after we spawn it and save our spawned actor in a variable spawn actor, I showed it before. You can see here equals null btr. And after we did it, we check if our spawn actor mm, is not isn't null. So if spawn actor contains something, some real actor, we can attach it to our endless generator class, which is on the scene. And after we attach it, we can just call the method of this spawn actor create mesh and put our map cache data using q item as a key inside these create mesh arguments. And this is all actually, all we have to do. Let's see again our structure, what actually fmap data is. Fmap data contains all these variables here, all these arrays for our generation, and two different how to say, constructors, empty constructor and the constructor with this how to say in English. So I hope you understand what I'm talking about. Actually, arguments. We'll say arguments, but that's not right actually. But let's say here, this method you don't need to use it. It's ignore just for now. And here we actually create our constructors. So outside this structure. That's all. Let's start our game. Wait a bit. As you can see, we can't see here anything. As you can see in my scene, I spawn my endless generator. You can see this class here. You can actually just drop this C++ class or create create blueprint class based on endless generator, for example. But I don't need it. Actually, I did it and put this C++ blueprint representation of the C++ class. And here you can see different settings. For chunk data, we can choose, as I said, our class we will spawn. This class is based on our chunk mesh actually. So I have C++ version and blueprint version. Anyway, here we can change our chunk size, grid spacing, and UE scale if you want. Here in terrain data, you can see that we can change seed, we can change different values for our noises, like octaves, frequencies, multiplicators of the height, and so on. And here, as you can see, we can change our render range. For now, it equals 30 chunks. It means that the radius of the generation will be 30 chunks. Here we also have can put our curves, and that's all. What is important is to go, for example, in blueprints. If you create the blueprint representation of a chunk, you have to change one thing here, because we use a material. We have to understand what material we use actually, and to understand it, let's open this blueprint representation. And as you can see here, we can see this raw material, and here we can choose our material. And if we want to see any vertex colors, we have to create something like this. So vertex colors, vertex color as a base color, and some roughness and specular as 0, for example. And as you can understand, if we start the game, everything will be just all right. As you can see here. Just all perfect, just perfect. And our endless world, clear and nice. Now ultra optimized. We can do absolutely everything with it. So, thank you for watching me. In the next part I will talk about the cache, actually the writing and reading data from this cache file. And so, goodbye.